So first of all, thank you, Dipendra and Raghunathan, for this invitation. It's an honor, and I'm very glad to be speaking here. So I met Harishchandra just once, but this was at the Boral conference, so several people were here. I was there as a graduate student, but I didn't manage to pick up the courage to say hi. And then, yeah, so I never spoke with him, but I did see him at the conference. Okay, so, yeah, and that's sort of been a regret. I wish I'd kind of said a few words to him. Okay, yeah, so, right, so okay, so it's not some results, I guess it's just two results. So I'm going to describe two results about double affine Hecke algebras. So the first result is a Coxeter presentation. Okay, so let me try to explain some things. So let G be an affine Kac-Moody Lie algebra. Okay, so let W be the Weil group. And, okay, let L be the co-root lattice. And let's look at the semi-direct product. I'll use some fancy font for the semi-direct product. And this is the double affine Weil group. So it's double affine because the Weil group of an affine Kac-Moody Lie algebra is already affine. And so we are affinizing it one more time, so that's why it's a double affine Weil group. Okay. No, I think this is the right way. Otherwise things get obscure at the bottom. Okay. So, so when you have a Weil group, then you can construct a braid group and you can construct a Hecke algebra. So this was done. So this is the braid group. And this was done by van der Leck in 1981, and let's write H for the Hecke algebra. I will explain these things. And this was done by Cherednik. I think around 1991. Cherednik explained how to construct the Hecke algebra for this double affine Weil group. And what I want to describe is a Coxeter. So this is not, this script W is not a, so what am I doing? I'm sorry, doing something wrong. It's crackling. Okay, so it's not a, Put it in my pocket? Okay, I'll try. यहाँ पे लगा दें, ठीक है पूरा? Should I put it in my pocket or on the belt? Okay. All right, fine.
Remove your glasses and any shawl that you are wearing.
I will if you remove yours, Dave. And the shoes. Okay. Okay. So the Hecke algebra was defined by Cherednik around 1990. And but the Coxeter type. Well, it's not a Coxeter group, so it's maybe not fair to call it a Coxeter presentation, but it's pretty close. So Coxeter presentation. So presentation. So this is the work of Bogdanian and myself. And it was published a couple of years ago in the Memoirs of the AMS. Yeah, 2021. So I want to explain what it is. No, maybe I should say. For all of them, okay, for W, B, and H. Okay, so let me consider. Okay, maybe I'll just explain the case of untwisted affine Lie algebras, which is a little bit simpler, but there's also a presentation for the twisted case, and it's in this paper. So today, let's assume G is untwisted. So which means G is affinization of some G naught. And let's say the Dinkin diagram So maybe I fix some notation. So let's fix simple roots. That's right. But it is the while group of an affine Lie algebra, and it happens to have a description as the affine while group of some finite dimensional. So then when I talk about the affine while group of affine Lie algebra, it's reasonable to call it a double affine while group.
But what is the translation subgroup?
It's the co-root lattice of the Kac-Moody. Yeah, but it's going to show up at some point. You know it well, so I don't have to explain it. Okay. All right, so simple roots. Let's fix some simple roots. Alpha 1 and simple co-roots. Yeah, and okay, so the usual convention is that these are the simple roots and co-roots of G0 if it's untwisted. Okay. All right. So now you have the Dinkin diagram. So it looks okay. So here is some finite Dinkin diagram. Something happens here, so this is finite. And then maybe you have something attached over here, something like some node 0. So there's an affine node. So let me just, okay. So it could be attached in two places, or it could be attached with a double edge, but this is just, okay, so let's do an example. So let's take, how many? 1, 2, 3, 4, 5, 6, 7. Okay, one more. So this is E8, and then I think that's where you, so how does the numbering go? Something 1, 2, 3, 4, and 0. So let's put a dotted, okay. Yeah. Okay. So B has this presentation, so you have generators. Let me go halfway up. Generators. So I want to take T1 through Tn. Those are for the finite nodes. And for the affine node, I want to take 3 generators. So you take 3 affine generators. Okay, and now what are the relations? So if I take any one of these T0i together with T1 through Tn, then that's an affine braid group. For all I equals 1, 2, 3. I need one more thing, so let theta be the highest root. So I have 3 affine braid groups, but there's one more relation, and this second relation is that if I take T01, T02, T03 together with Ts theta. So Ts theta is the element in the finite braid group, which corresponds to the reflection S theta. Then this is some Q inverse, which is central. And the point is that it's central. So it's okay, and that's all. So those are all the relations here.
What is Q?
It's some central element. Yeah. It corresponds to the exponential of k, which is
It's also in the center extension.
yeah. Yeah. Absolutely. Yeah, it's a null coroot. It's the exponential of the null coroot. Okay, so that's the description of the braid group.
You mean alpha I check alpha I?
What? Oh yeah, thank you. Okay, now to define yeah, maybe I should well, okay. If I could stick in Q over here, and then this relation means this. Otherwise, this is the definition of Q. Okay, so yeah, this is for the untwisted case. In the twisted case, you need it's slightly more complicated, but it's explained in our memoir. Okay, for the Hecke algebra, so you choose parameters. Okay, so you take some field f. So if I have some f is some field, so I choose T0I and then Tj. Those are some. Okay, let's use K. Those are some elements in F cross. Then the Hecke algebra with yeah. Okay, and Ki is supposed to be Kj if Eric used this term, which I like, if I and j are in the same one connected component. So these are some nodes of the diagram, and if you have, unless you have a single edge, there is no restriction on these parameters. So you drop all the multiple edges and then look at the connected components. And for each of those, these parameters have to be constant on that. Of the Dynkin diagram. I just explained. So, I mean, if you have some diagram,
I understand.
you cannot read what I'm writing?
No, I understand. I understood your explanation.
Equal. Sorry. Thank you. The equivalence means equal. Ki is equal to Kj if I and j are in the same one component of the diagram. Okay. So that's so. What? No, there's some things in some invertible elements in some field with this restriction. Yeah, maybe I should write choose such that. Pick a field, pick parameters in the field, in invertible things. And let's call this whole collection K. So then I can define HK. So K is this. K is this set of parameters. So HK is you can take the group algebra of the braid group, and you impose relations like Ti minus Ti inverse equals Ki minus Ki inverse, and similarly for 0i. So that's the double affine Hecke algebra. Yeah.
This is good. The relation to the equality AI runs over the second set of parameters. Right? K0 is the not solved.
No, I said also for. Similarly, you impose the same thing. What? No, you impose this condition for all I. The ki's happen to be equal, they happen to be equal. Is it clear?
Essentially, when the K0i is the same as K0j.
No, I'm not asking that.
Oh. Yeah, I mean, okay. Fine. I mean, here, okay, fine, here. So K01, K0i would be the same as K8. Because they are, if it's connected by one edge, then it has to be equal to. Okay, so the only time the K0i's come into play is when there's a double edge, and this is what leads to these Kornwinder story. Okay, yeah. So I should really use some other letter that's going to run over the i's and the zero i's, because everything is being said for all of them. What?
In this specific example, all of them are one character.
In this case, yes. There's only one parameter, and that's because the affine diagram is simply laced. Okay. Yeah, this is sort of. So okay, and so this is the Hecke algebra. And of course, if we put, if I just set, okay, so the physicists use I, okay, so I is this index set. So I will use capital I. So I've been talking to physicists, and they just make up something. And okay, so if I just put Ti squared equals, so if I just look at B mod Ti squared equals 1 and Q equals 1, if I just quotient this, then this is that guy. So, in particular, we have a presentation. I don't want to put Q equals 1. Yeah, I don't want to put Q equals 1. I just need to quotient by the quadratic relations. Then that's a presentation of this double affine of the double affine Weil group. So, it looks like a bunch of three affine Weil groups struck together along this central relation. Okay. So, is it clear?
What is the meaning of DI?
Huh? Oh, I is an index. So instead of writing 0i and little I, I'll just write capital I, so it runs over this set.
Individual square or
What?
individual square?
Yeah. Just set all of the squares of the Ti is equal to 1. Plus you impose these braid relations, and you set the squares of generators equal to 1. That's a presentation of this double affine Weil group. So that's a calculation you can just do. Okay. I should say that here. So here now it makes sense that I should say what is Q in this setup. So Q would be e to the minus k, or exponential of minus k. where k is the null root. Null coroot, sorry. Yeah, null coroot. Okay. Okay, so, right. So, all right. So, so if I just take, okay. So let's write, maybe I don't want to put a subscript. I want to put an h of something. So let me put hi to be this affine Hecke algebra generated by T0. So there's three affine Hecke algebras. I'll pick two of them. So okay. So each of these looks like a finite Hecke algebra smashed together with the group algebra of a lattice. So H1, I'll just, yeah, this looks like some, okay, H0 would be when I just take, maybe I write it like this, okay. So H0 is generated by T1 through Tn, and Hi would be generated by T0i and H0. Let's take those subalgebras. For this is I equals 1, 2, 3. So H1 has a description. H1 looks something like this, and H3 also looks like this, where X and Y are group algebras of two lattices. Two lattices. That's a description of the affine Hecke algebra. It looks like this. And so in this algebra H, I have these two lattices floating around inside this algebra. And this is important in what's called the polynomial representation, or maybe the Dunkel-Cherednik representation that Eric talked about.
Sorry, is each of these lattices isomorphic to the finite group lattice?
No, it should be, okay, in this setup it should be isomorphic to the coroot lattice. Yeah, I think. It should be the coroot lattice of G0.
I just wondered because at the beginning you were drawing the coroot lattice.
I did. Yes. Yeah. But this is a slightly smaller lattice. It will. Okay. Maybe I should write y0 and x0. Two finite coroot lattices. Is that better?
I don't know. I haven't understood at all.
So one of these, I think this maybe H1. Okay, I'm saying that this is isomorphic. I didn't give some explicit isomorphism. Then in the isomorphism, one of these groups, I think H1, or B1, if I were to define, would go over to W.
I mean, the 1, 2, and 3,
Yeah.
those three things, I understood your explanation to be that they were isomorphic.
They are. This is only in the untwisted case, which is where I am talking about.
And so these extra lattices, X and Y,
Yeah.
they are isomorphic.
They certainly are, right. But in this isomorphism, so I wrote this is equal to, I should just say, this is isomorphic to. And in the isomorphism that I write, one of these, okay, so in the untwisted case, okay, maybe I should write something here, which may help. So what is true in this case, that Q check, so L, I called it L, right? So L is isomorphic to Q0 check plus Z times K, where Q0 check is the co-root lattice of G0. So on the face here, you can see that this is W0 semi-direct product Q0 check semi-direct product Q0 check plus ZK. So you see two copies of the lattice there anyway. Okay? And that's basically 1 and 3. The lattice 2 is kind of hidden in there, and when you make it explicit, the description becomes simple. So this corresponds to 1, and this corresponds to 3, or maybe the other one. Yeah. But there is a third lattice in the middle, and it wraps together in this central relation. Any other questions?
Is H not
H naught? Sorry, okay. So, H naught, no, H naught is it's the Hecke algebra of the finite while group, which I'm calling here W0. Okay, so there's a finite while group, then there's an affine while group, and there's a double affine while group. And yeah, and maybe this description is good. So somebody asked, okay, you asked, right? So, yeah, this there's already co-root lattice, and now I'm adding on the co-root lattice of the affine Lie algebra, which in the untwisted case happens to be just another copy of the inside lattice plus Z times the null root. But in the twisted case, it'll be different. These two lattices would actually be duals. It's a little bit more intricate. Okay. Any more questions? Okay. So, how much time do I have? I started at 11:10. Okay, so I'm like halfway through plus 5 minutes. Okay, good. Yeah, okay, so, all right, so now let me just, so this is all I want to say about the presentation. Yeah, so there are these two lattices inside here. Okay, and now let me talk about representation. So I'm going to describe something that we call the quasi-polynomial representation. So this is a joint work with Jasper Stokman and Vidya Venkateswaran. Okay, it's not going to fit. So. I didn't realize it's such a big word. Okay, long word. Okay, fine. So first, let me recall what is the polynomial representation. And this is due to Cherednik. What it is you take a character of H1 and you induce to H. So it's induced from a character. So it's, this has a Coxeter representation, and you can set all the Ti is equal to Ki, let's say. So this defines a character, and you induce this from the character. So this is 0, 1, 1, 2, 3, 1, 2, n. And you can actually realize it on the group algebra of the lattice X. Well, X is already the group algebra of a lattice.
Sorry, I don't understand this. Ti, Ki, what is Ki?
Oh, Ti's are...
I understand, but what Ki?
I is in this set.
What is Ki?
K sub I were these parameters that I chose.
What is a map Ti? Well, Ti gives Ki. Why? This is the character.
This is, I'm defining a character. Sorry, is it clear?
No.
Sorry, yeah, I forgot to write. This is clearly a character, you can check. Then you induce this character, and now you get a representation, and you can realize it on X. And this is the polynomial representation. On X0. Well, okay, maybe you also need to include Q. So, okay, maybe I would say this. group algebra of L. Because I also want to have K in there. So you can realize it on the group algebra of this co-root lattice. Basically what you're doing is you could induce the trivial representation of W up to the lattice. But instead of that, you're taking the character of a Hecke algebra and inducing to the double affine Hecke algebra. And that's the polynomial representation. Okay, so now it has formulas. So I can use, I can write x to the lambda, so c to the L, okay, maybe I should say c to the L is just the, oh no, not c, f. I have some field, and sometimes I want the field to be some field of parameters. So I don't want to work with complex numbers. On this group algebra, so the formulas would be, okay, so f of L is just some span of things like x to the lambda, lambda in L. That's what the group algebra is. It's just combinations of these. I'm calling these things polynomials, although as Laurent pointed out, they are Laurent polynomials. Right. Okay. But that's okay, I will just call them polynomials. So the formulas are, so here, okay. So I have here, I can write here, okay, so the first point is that your algebra H is also generated by H1 together with, okay, let me call this X. So this I called X0, but I will call this X by X. Okay, so X0 is part of X. So the formula is, so I have, okay. Let me just, so instead of writing all the time T01, so I will just write T0 for T01. Okay, that's those are the elements in here. So then I can just write Ti of, let's write this formula correctly. First I have these, so I have x lambda, so it's realized on x. So x lambda acting on x mu is just x lambda plus mu. Okay, let's call this representation pi. So pi of x lambda acting on x mu is just translation. And so this lattice part just acts by translations. And then pi of Ti acting on x mu is Ki times x to the Si mu plus Ki minus Ki. This is the kind of the big thing, so let me write it. Plus Ki minus, minus 1 minus x to the alpha I mu divided by 1 to the x minus alpha I check times x mu. Times alpha I check times x to the mu. Okay. So let me take a moment to explain this. So these x to the alpha I checks, they are in the co-root lattice, right? So this is an integer. This is an integer. So this expression is going to be divisible by this expression. And so this quotient will be some element of the group lattice, and you multiply x mu by that. So that's two terms. So this is an example of a divided difference operator. Yeah? Okay. I mean, this is a little bit complicated, so if somebody wants to ask, I would be happy to be slowed down a little bit. Yeah.
By looking at the double affine
Yeah.
that is just the finite part and the L part.
No, it's the affine part and the L part.
Okay, affine part and the L part, and affine part giving H naught.
No, affine part, no, the affine part has a finite part and another translation. That's why it's double affine.
So if we add this Y naught, then this affine part will come. I mean, H naught and Y naught.
I'm not sure I understand the question.
The question is that corresponding to W, there is some sub-algebra.
Yes. So this subalgebra that corresponds to W is exactly this H1. Yeah. And what corresponds to L is this thing that I'm calling X.
That one is commutative. That X is commutative.
Yes. Yeah. X is a group algebra of some lattice.
This final formula is somewhat similar to how one would look at for pi hat formula. There's something like a denominator which is how we'll be getting things in the denominator of pi.
Yeah, this is right. This kind of divided difference operator shows up in many cases in p-adic. Is it related to the Weil character formula? Probably, but it's some distance from that. This is some non-symmetric thing.
So can it happen that U of orthogonal to alpha?
Yeah, then you get 0.
So then it's x and 0.
Yeah. It can certainly happen. Okay, so this is clear, right? I mean, if there's more questions, please ask. Because I'm going to make it much more complicated. So I would like to handle some issues here when I define the quasi-polynomial representation. So basically, you have some structured theory for this double affine Hecke algebra. It has some Hecke algebra. It has an affine Hecke algebra. You take a character and you induce. And what I'm saying is that what the representation can be realized on this lattice. And here is the formula. If you flip what?
The relation.
What does it mean to flip?
And X mu dot something di.
Yeah. Right. Maybe I should use a different letter for the. So this is an element of the Hecke algebra, and this is a basis vector. Okay. Same way. Say it again. Oh, no, it's only this guy is acting. So this is I equals 0, 1, 1 through n. The action of the other T02 and T03 is more complicated, and I'm not writing it down. But this is enough because these guys generate. Okay. Yeah, please ask, because I'm probably not giving some optimal presentation, but I hope to be able to answer any questions. So if you see some issues, please. Okay. Is it good? Okay. So now I will explain the quasi-polynomial representation. So these were some parameters, right? So the Hecke algebra and the polynomial representation, they both depend on these parameters. So for this quasi-polynomial representation, I have a richer space of parameters. This is with Vidya Venkat. Jasper Stockman. Okay, I guess I come first. And we have two papers, one of which has appeared in Selecta. In 2022, and then the other one, so that's one, and then the other one is a preprint from last year on the archive. Well, also from 2022, but okay, fine. So archive. Okay, so yeah. So so I have to tell you what is the so first I should tell you what's a quasi-polynomial. So let V be this lattice X tensored over Z with the field. Okay, I need some assumption on field, so the field is characteristic 0 or something. So I take such a vector space. No, I don't need to do that. I will rather take L tensor over Z with R. So it's a real vector space. So I just work with, I tensor the lattice with R. So this is the part of the tan of the Katsuri-Lie algebra, not including the derivation. Okay, and then I'm going to take the group algebra, quasi-polynomial, that's really the group algebra. It's the space of quasi-polynomials is just the... So it's just some finite combinations of x to the v and v, and over f. So instead of, what's a polynomial? Well, a polynomial is where instead of v you have L, you have a lattice. The quasi-polynomial, it's just, it's the group algebra of the additive group of the real vector space. But any finite combination. So this is the space of quasi-polynomial. So let me just call it Q. Okay. So now G, okay, so so this quasi-polynomial representation depends on some parameters. So what is the space of parameters? Well, its functions, let's maybe say phi is the root lattice. Is the set of roots. Phi is the set of real roots of the affine Lie algebra. So the parameters are a function. So there's some f from S1 to f cross. So S1 is just the circle. And so that's the space of parameters. So previously the parameters were some function from phi to f cross. Now it's phi times S1 to f cross. And the conditions are, so G of W alpha, okay, so first, G of W alpha Z is G of alpha Z for all W in the affine while group. Okay, so it's some W invariant in the first coordinate. S1 is the set of Z such that just the complex numbers of modulus 1. Okay, so G W alpha G is this for all W and for all alpha for all Z. The second condition is G alpha of Z inverse is G of alpha Z inverse when Z is not equal to 1. And 3, G of alpha comma 0 is just K alpha if W, if alpha is W alpha I for some W. So it's just Ki. Okay. You're puzzled by something? Huh? No, not 0, 1, thank you. So at the identity, the parameter is the k parameter from before, but elsewhere it satisfies this condition. Okay, so yeah. So the following no, okay. I want to do one more thing. I want to put gi of v, yeah, gi of v is g of alpha I times alpha I paired with v. No, e to the 2 pi I. Okay, let me use j first of all, so that doesn't conflict with the I. Okay, so I have, so the g is a function on phi cross S1. I want to define a function on this vector space V. And the way I do it is g sub j would be I evaluate my function g at alpha j and 2 pi I, e to the 2 pi I of alpha j paired with v, which is some real number. Okay? And so if v is in the lattice, then this number is 1, and I just get ki. But if v is not in the lattice, then this is something else. Okay. So the following defines a representation pi g of h on the space of quasi-polynomials. So pi g of x lambda on, okay, so now here things are going to be x to the v. Yeah, those would be elements of this space of quasi-polynomials, and it just acts by translation. So how do these, what's pi sub g of ti acting on xv? So there are two parts, and they both change a little bit. So the first part just becomes giv x to the siv. So this ki became a gi. And what about the second part? So plus ki minus ki inverse, and then 1 minus x to the alpha iv times alpha I check over 1 minus x to the alpha I check times x to the v. And now this doesn't make sense anymore because this is not an integer. So you just put the floor function in there. Okay. So this defines a representation of this. Okay, so I think I'm out of time, but this representation has to do with the Weil group multiple Dirichlet series. Or I should say, this has to do. This representation has to do with. Okay. Has something to do with. So I don't have time to explain. Equivalently, with the Whittaker functionals, or Whittaker functions, for unramified principal series, Ihori Whittaker functions. Series of for covers of reductive p-adic groups. So those Whittaker functionals for these metaplectic, I guess in this theory sometimes they're just called metaplectic covers. If you take Whittaker functionals for those can be understood in terms of this representation for some special choice of G which corresponds to Gauss sums. Take a look at the paper. Who's asking? Yanis? Yes. Okay. So for you, the point is that Macdonald polynomials have something to do with Whittaker functions. So here I can. I didn't get to it. So here you can define some quasi-polynomial generalizations of Macdonald polynomials. And those you can specialize to recover Whittaker functions for symplectic covers, metaplectic covers of p-adic groups.
What is called the Kastelman-Shalaika formula?
Yeah, something like some version of the Kastelman-Shalaika formula, but for metaplectic covers.
At the moment there is no Kastelman-Shalaika covering groups.
Okay, but this will give some formula of that sort. I think this formula is sort of known somehow. So the Whittaker functions you get when you you have to kill one parameter from Macdonald polynomials to get to Whittaker functions, and similarly, if you kill this parameter here, you get these Whittaker functions in the limit, and they, for special choices of G, this G, right. When you choose this G according to some Gauss sum, then the Y eigenfunctions that you get here would be would correspond to Ivahori Betikar. Yeah, that's.
Or specifically, you recover someone for them.
Huh?
There have been various works computed with Ivahori.
Yeah, this is okay. So this would recover in this limit the work of Chinta and Gunnels and Pushkas. That's some precise statement. This understands it sort of at the level of the double affine Hecke algebra. Yeah. But from the point of the double affine Hecke algebra, this led to the discovery of this representation, so to speak.
Any questions?
Yeah.
Is there a nice description for the center of this Hecke algebra?
The Hecke algebra didn't change. It was the same description as before. I'm just changing the representation.
Oh, I'm asking about the center.
The center of the double affine Hecke algebra, yeah, I mean, we know generators and so on, but the relations are very complicated. Yeah, I think, yeah, that's true. I mean, in the case of this affine while group, it would correspond to W invariant things on L. Some W invariant polynomials in L. So there is some version of that here. I mean, in Erik Opdam's talk, he talked about the spherical Hecke algebra, and that would be a limit of this thing.
But I thought that the center of the double affine Hecke algebra for generic parameters.
No, the center of the affine Hecke algebra, right?
Yeah, fine.
Yeah. Sorry, were you asking affine or double affine? Double affine, yeah, there's not much there. What is there is that there's an action of a congruent subgroup. So in this description there was T01, T02, T03, and there's a sort of a free group of T01, T02, T03, and that has an action of the braid group of the braid group on 3 strands that acts on the free group, and the action descends to an action of SL2Z in the outer automorphism group. So some outer automorphism on the double affine Hecke algebra, an action of SL2Z. In the twisted case, it's a congruent subgroup. Think of level 2 or level 3. You can see that from the presentation, from the Coxeter presentation. That's one of the things it's good for. So I think gamma 1, 2 and gamma 1, 3. Yeah. Yeah, for affine, if you have affine 2 and affine 3, then in this book gamma 1. Here we have an action of those by outer automorphisms on the double affine Hecke algebra. You can see that from the Coxeter presentation. Otherwise it's hard to see, very hard to see.
So let's thank Professor Sahi again. Prameya has some announcements to make.
Yeah, so